Having examined the implementation of binary trees and binary search trees, let's now consider two applications. The first application involves using a binary tree to construct an arithmetic expression tree. Arithmetic expression trees are proper binary trees. Recall that being proper means that every node has either two children or no children. Nodes that have two children, which are the nodes that are not leaf nodes, are called interior nodes. In an arithmetic expression tree, the interior nodes contain operators. Nodes that have no children are the leaf nodes, and in proper trees are also referred to as exterior nodes. In an arithmetic expression tree, the exterior nodes contain operands. Once we've constructed the arithmetic expression tree representation of an expression, we could use the binary tree traversals to generate the expressions in each of the three expression formats. Doing a pre-order traversal of an expression tree produces the expression written in prefix, with the operator before the two operands. An in-order traversal renders the expression in infix notation, and a post-order traversal generates the expression in postfix. The correspondence of the prefixes is, of course, no accident. Let's examine the various classes that are needed for this example. The arithmetic expression tree class is the class that defines the expression and has methods to construct a tree from a string, transform it into either prefix or postfix, and to evaluate it. It is a subclass of the binary tree class, so it inherits the node structure of a binary tree and the three binary tree traversal methods. As we've done with most examples, we provide a GUI interface defined by the expression GUI class. The expression must be input in fully parenthesized infix notation. Input that fails to conform to that syntax results in the invalid syntax exception being thrown. We've elected to explain the most interesting method in the arithmetic expression class, the makeNode method. It's a recursive method that constructs the tree. The method is supplied the string tokenizer object that contains the expression and returns the root node of the tree. If the expression is not syntactically correct, it throws the invalid syntax exception. The string tokenizer object has the four operators, two parentheses, and a space as the delimiters. Because spaces are the one delimiter that we do not wish to treat as a token, we provided the next non-blank method. It returns the next token that is not a space. The isOperand method checks whether the next token is an operand. If so, it returns a node containing that operand. This is the base case of the recursive method. The recursive case checks whether a parenthesized subexpression is next. So the next token must be a left parenthesis, or the syntax is incorrect. Recall that this program requires the expression to be fully parenthesized. Then a recursive call is made to parse the subexpression that will become the left child of this node. The next token must be one of the four operators, or the syntax is invalid. Then the second recursive call is made to construct the right child node. Finally, there must be a closing right parenthesis. And the final step is to construct the node from the two children and the operator and return it. Okay, so let's run this program to get an idea of how it works. And I've already input an expression here so that I don't mistype anything. And I've included all of the four operators. I've also, in some cases, put spaces, in other cases, in this case, for example, no spaces. With an infix, fully parenthesized infix expression, you don't need spaces anywhere, but you can have them between any of the tokens. All right, so I'll press the Make Tree button, and it indicates that yes, the syntax was okay, it was constructed. So now we'll do the evaluate, and you can confirm that indeed 13 is the correct value. Translate it to prefix, and notice the operators come before the operands, and postfix where they come after. So let's do something just to test out some of the checking of correct syntax. So let me remove one of the parentheses. And we get an error message that says it's an incomplete expression, which indeed was the case. So let me put that back, but try something different. Let's put in an invalid operator. So the remainder operator was not one that we allowed. When I do make tree, it gives me invalid operator. Okay, so now the next example. This second example involves creating a sorted set from a binary search tree. The TreeSet class implements that sorted set, and it contains an instance variable whose type is binary search tree. And as we've already seen, the binary search tree class is a subclass of the binary tree class. There are two exceptions that the TreeSet class can throw. The duplicate key exception is thrown when adding an element that is already in the set. The not found exception is thrown when attempting to remove an element that is not in this set. And as always, the interface is defined by a GUI class, in this case, TreeSet GUI. The one class in this program that we're going to examine is the TreeSet class. TreeSet is a generic class whose components must implement comparable because it's represented with a binary search tree. So the type of the set instance variable is also binary search tree. The insert method is given the element to insert, and it calls the add method of the binary search tree class. If it returns false, it means the element was already in the tree. So it throws the duplicate key exception. The delete method is provided the element to delete, and it calls the remove method of the binary search tree class. If it returns false, it means the element was not in the tree. So it throws the not found exception. The element of method is past the element that is to be tested to check whether it is in the set. It calls the contain method and returns what was returned to it. Okay, so let's run this one. And this is in the TreeSet GUI. And when I run it, it's going to ask me whether I want to initialize from a file. And I'm going to say yes. I've created a file that contains some Greek letters. So we'll notice that these are already loaded. So this is what's currently in the set. And now I'll try out a couple. Let's try out, there's 3 different operations, so we'll try each of them. So let's begin by attempting to insert the letter pi. And of course, it's inserting these in alphabetical order. All right, so when I process that request, we notice that it's inserted in the correct location. Next, let me try to delete something. So let me delete gamma. And when I attempt to delete it, it is gone. So let's try some of the error conditions. Let me try to input something that's already in there. So when I do insert, since beta is already in there, I should get the error, which I did get. Beta is already in the set. And similarly, let's try deleting something that's not there. So let me try to delete alpha. And when I do a delete, alpha was not deleted. It's not in this set. Okay, then the last one that I'll test here is element of. So this is going to check whether or not it's in there. So let's try both situations. Let's put in delta, which is in there. And except I misspelled it, so it's not in there. Okay, so let me spell it correctly. And hopefully in this case it should tell me yes indeed that it is there. Okay, so in this case now we've tested all the operations for both success and for failure.